So my name's John Mitchell. I'm a senior lecturer here in the department. And sort of following on from some of the things that we've talked about already, looking at, well, what is going to sit underneath? But we start from a point that I think Misha talked about very nicely of 5G is not going to be the sort of thing that we knew about before. It's not going to be one sort of technology. It's going to have a wide variety of technology. We've already seen the sort of headline figures of 1,000 times increase in data rates. We're talking about million times increase in devices across the world as everything is connected. So what's going to sit underneath that? What is an architecture going to look like that is going to be able to cope with these multiple different things? And I think one of the points that came out in the previous talk is it's not going to look like the traditional architecture. The core network we had followed this rigid pattern of being quite a prescribed and centralized core that was put there because that was a pragmatic solution. It was the way that we'd always built networks, and we continue to build networks in that sort of way because it's what we understood. And despite how we look at this technology, I think the only thing we can see is that it has on the face of it got considerably more complicated. And so we, at least from an architectural point of view, there's always been the conservative element of trying to stick at least with what we know sitting underneath. And you see the bottom half of this iceberg of this technology that sits underneath that is reliable and that we can trust. But when you compare and contrast that with the Wi-Fi networks and those consumer networks that we understand, where it's a best effort network that we know very little about, and just we consider it as a native transport that will get our packets across the Ethernet's case and the Internet's case as best as possible. We may not be able to rely on that sort of network, but actually some sort of decoupling of being able to have a core network that is multi-purpose is going to be a big driver within 5G. So I'm going to draw a lot from what's already happening in true 4G. As we said, what we see as 4G is not quite there yet, but there's many things coming through in 4G. And these are all going to be played out on a large scale within 5G. And so looking a little bit at some of the work we've been doing about how a technology of front hauling is starting to be introduced, and we're already seeing some of these solutions. There are issues. It's generally, certainly operators are saying that it's not cost effective yet. And that's partly because some of these cooperative advantages that we're going to need to see to provide this much higher bandwidth and this much higher availability of devices are not fully played out yet. And so the advantages and the requirements are not quite there. And then particularly talk about what the challenges are with the current solutions, and actually plays to that last point of, well, is there a point to be an analog? We've traditionally gone digital, but is there room for analog in such a network? So some of the things we're seeing are not particularly new. There's been a community, the radio over fibre community, have argued for separating out the network to a transparent front end and centralising much of the processing for some time. But this community has never gained a great deal of traction. It's always been a step behind the standards, a step behind what's happening in the community. And every time a new standard comes out, it tries to muscle its way in. I've been part of this community for 15 years, and it has invariably failed. Partly because it's driven out of the optics, mainly led out the optics community, and the crossover into wireless has been very difficult. But the argument is an argument that is now starting to play out. The idea that why would we put all our expensive electronic equipment in a hut in a field somewhere? Where does this make sense from an architectural point of view? We put more and more equipment out in this little box here that we know has engineering challenges. If you've ever tried to make something water ingress proof, it's surprisingly difficult, as well as trying to power it, trying to environmentally control it, air condition, all those sorts of things are very difficult. So the argument has generally been, well, can we move some of that fancy stuff further back into the network? Well, the idea that has often been proposed is as soon as you're starting connecting these with fibre, Actually, if you look at this example, there's a microwave dish on the side of this, so this is obviously not a fibre-connected base station. But if it were, why do all this here? Can we not move that back further into the network? Simplify what's going to be out at the front end and make that as much of the edge of the network transparent to modulation format, to frequency, if at all possible, quite a wide range of frequencies, and keep this as simple as possible. And do all the clever stuff further back in the network, transporting those signals over a fibre network. And this slide I've been using for 10, 12 years now, and lots of people have talked about it and never got that far. Until the last 3 or 4 years, where the concept of front haul has started coming through, but done in a rather different way. So the idea here is this is what this would typically look like. Maybe fibre connections, microwave connections out to these little base station huts, and before the coaxial feed up to the fibre, up to the tower. We've started to see that these are being replaced with remote radio heads. So the very last part of the electronics that are here is now moved much closer to the antenna. This means the sighting of these devices, rather than having to be right next to the tower, can be moved slightly away. You can ease some of your cell site problems, and usually a fibre link delivering the radio signals to be converted, amplified, and spat out. So moving the remote radio head right close to the antenna, fibre link to your baseband unit, and then still microwave or fibre data back into the network. And these have been now quite widely deployed in newer antenna sites. Of course, it begs the obvious question. Well, this was close because I had a coaxial link. In fact, I got it very close. We've eased that a little bit by having fibre, but we all know fibre can go a very long way. We have fibre across the Atlantic. People have shown radio signals over fibre of hundreds of kilometres. So what use is this building here now? Why could we not do away with that completely? And that's the concept that starts to lead us towards the idea of a cloud radio access network. That we're going to pool a lot of our baseband units, our processing, at a central site. Maybe these will be clustered, serving a small number of cells and still backhauled to a central office. Maybe this will be co-located with the central office, if you like. And use fibre feeds to feed these networks. Now, if we could develop a network like this, we could have high transparency, so that our network is now not defined by the amount of equipment that we put in a cabinet at the base of each antenna. Our capacity in our network, the frequencies we use, the number of channels we allocate to our cells, can be defined at a place where we have statistical multiplexing of equipment, and we can have advantages. And so the idea that we can have greater flexibility of the front haul of our network is very appealing. So what does this actually look like? Well, we've gone from this sort of model where everything's here, and we have to think about all the things we needed in this cabinet. Air conditioning. So you look at many mobile operators will suggest that this is 30–40% of the energy usage of this unit here. Uninterruptible power supplies to keep this going in event of a failure. Bulky, expensive, difficult to maintain out in the field. And all our baseband processing units, our backhaul units, and our remote radio heads linking up to our antennas. So if we shift these blocks around, we can put a much simplified front haul network, conversion from the radio signal to some backhaul signal, links over fibre, and all our baseband processing and our backhaul into the network is shared at a central site. So now we've gone from quite a large and expensive unit here to a much more highly simplified unit. Potentially even something that could sit with the remote radio head up on the top of the antenna. Maybe not even needing a separate site, although for pragmatic reasons, that's still a bit of a push in its implementation. So this model doesn't seem to differ too much from the one I started with about the analog model. But there is a key difference here. The way this is typically being implemented, even for the remote radio heads, but certainly the early Cloud RAN trials that a few operators have been doing, is that this interface is digital. So it uses generally a CPRI standard. There are two other standards, but very, very rarely used so far, to actually transport this as a digital link. And so we end up with a network that looks something much more like this. So our front haul network, radio heads to a baseband pool, clustered for clusters of cells perhaps, and then our aggregation network back to the gateways that were talked about earlier, mobile management entities, these parts of the network much further back. So maybe this starts to make you think about some of the other advantages. If you think about how an LTE network is formed, one of the things that happened with LTE is that these start taking a little bit less of a prominence in the control. You don't see a base station controller unit. All that base station control is actually done at this point here. Now that has advantages, getting that processing much closer to the units, the idea of being able to communicate between them, but we're back to our latency issues. We're back to communications issues, much based around this X2 interface. Now, so this is an interface that links the various base stations together. And for any type of joint processing, communication between them, the latency and capacities of these links starts becoming a critical factor of how, when you have distributed control, how messages are passed between those distributed units within your network. Obviously, this is simplified if now all these base stations are in one single point. We've now not got multiple links. And if you start looking at the LTE networks, you'll see a mesh of these X2 networks, X2 channels between all the base stations. So having dedicated mesh between base stations is both a costly and slightly messy thing to have to do. The S1 interfaces back into the network can also be simplified, but that's not so much of a huge deal. But how each of these, what would have been separately located base stations, communicate can offer real advantages to what we can do. So just to summarise some of that, what might a Cloud RAN give us? Well, ideally reduced equipment at the cell site. So we've gone from our cabinets, our air-conditioned, our uninterruptible power supplies, to much more simplified units out in the field. And that has all sorts of benefits for the environmental conditioning, the difficulty of running power. You know, you talk to Vodafone, they'll say there's parts of the world where they spend an absolute fortune of their operating costs shipping fuel oil around to power generators to run their base stations. Now, anything that can bring that down has a significant impact on the operational cost of your network, and with those power consumptions. Also, potentially, much better load balancing and sharing of equipment between our sites. If we have now a virtual pool of equipment that we can allocate on need, we have much more flexibility of how we can allocate things within the network. We have a much simpler X2 interface, and I'll talk about what that leads us towards a little bit later. So this is all enabled by this concept of front haul. So that's the idea of a Cloud RAN, the idea that we've taken the way LTE has moved in the idea of a network of distributing some of this control, but formed it into pockets, clouds at the edge of this network, where our fundamental functions of that front part of the network are now aggregated. Rather than being aggregated at the base station, they're aggregated a bit further back. So I'm going to say a little bit about some of the technologies that we might use to achieve that, because there are examples out there already. There are some that are being deployed and some that are being trialled, and some that the research community is still very interested in. as I say, they're ones we've been interested in for a time, and I very conscious of the comment earlier about some of these technologies academics love because they're really handy to publish on, and whole journals of interesting yet useless technologies are abound. I think Elsevier has one, but there are specific advantages. So if we look at taking from a standard distributed system, you could move to a system where we now digitize at the front end. But rather than having our backhaul at the front end, at the cell site, we're on a CPRI interface. So we've digitized our signal, or we're going from analog to digital, and we're transporting the digital version of our waveform over an optical interface. Now, although some of these data rates start to look a bit scary, even 10 gigabit cards are certainly in commodity use. 10 gigabit optics is a couple of $100 now, not a great deal for these types of systems. We do have issues on latency, and these are some of the maximum latencies. It gets even tighter if you're trying to do some of the control circuits or move to tactile. As well as the qualities required. For most people in the optics community, this is now quite a scary number. It takes you back about 15 years. The optical community made a shift to wireless when high-speed forward error correction came out about 6-7 years ago. You go back 12-15 years in the optics community, these were the sorts of figures of bit error rate that we were being talked about. Now, 2.5 times 10 to the minus 3 seems to be standard, but actually now we're talking back. Why without FEC? It's what was talked about earlier. How do you put FEC in and achieve these very low latencies? Any stage of additional processing starts adding latency in, which is unacceptable in these sorts of networks. The alternative to this is to go analog and to say, well, I've got analog RF signals here. Could I transport those RF analog signals over the optics? Well, yes, technically you can. There are linearity issues that you don't have with digital techniques. There are noise issues you don't have with digital techniques. But there is a whole body of knowledge of this. There are journals, conferences. There's been a huge amount of work. So what's the advantage? Well, now I've not inflated my signal by digitizing it. One of the errors that I'm sure none of the MSc students here made, but the idea that digital is narrow band, well, no, as soon as you digitize anything, you blow the bandwidth up out of all proportion. You often get back again by some form of compression, which is easier in digital, but I saw at least that mistake once in the ITN exam this year. But here, you've got 100 meg. If you want to take a 100 megahertz channel, 200 megahertz channel, pick that whole channel off that may have multiple users, multiple carriers in it, I could pick that all up and transport that all back with relatively straightforward optics. And actually move even more of my processing, the digitization stage, further back into the network. Because although digitization techniques are fairly standard, they don't run that cool. There are issues, and there are, particularly when you're looking for the high quality stability issues, that still mean it's not entirely obvious you want them in the field. I'm sure it's not beyond engineering to make that happen, but it's not a simple engineering task. There are some challenges. Now, this works well for one antenna, going to MIMO, going to multiple antenna systems, massive MIMO type systems. Again, there are some engineering challenges there, but still not beyond the wit of man. So why do I say analog might be beneficial over digital? Well, let's look what happens when we digitize. So we take a 75 megabit per second signal. Standard sort of medium rate, low rate LTE signal. We're going to digitize it. CPRI standards specifies 15 bits, 30 megahertz sampling. So I digitize it on the uplink. I So deliver it, I've modulated onto my carrier, whatever my carrier frequency is going to be, and I transmit it. If I'm going to do this digitally, I'm going to essentially break the system with this CPRI interface to frame it and send that over fiber to my remote node that just takes the digital, converts it to analog, up converts it. Probably there'll be a high power amplifier here, spit it out. So what happens in this middle part here? Well, I've got 30 megahertz sampling frequency. I have an I and a Q signal. I'm going to have 15-bit resolution for my signal, and my CPRI interface specifies an 8B, 10B encoding to make sure I've got my synchronization. I can synchronize well. Because one of the requirements of this is very, very high tolerance to synchronization issues. So I need to have good synchronization between these two. So I've already got, for my 75 megabits of data that I'm providing to the user, I'm well over a gigabit already. Okay? And that's for one antenna, one sector, one MIMO. That's just one channel. So if I want 8 MIMO, 20 megahertz, I'm nearly 10 gigabits just to provide me with a couple of hundred megabits at the interface. So by digitization, I've exploded this. Now, there is one area of quite intense research at the moment, and some very interesting things starting to come out about compression. But again, we're back in that cycle of, yes, we know very good compression algorithms. We can take 400 megabit raw video and squash it down into 20 megabits. That's fine. We've been doing that sort of thing for a long time. But if you've ever watched digital TV and someone next door is watching analog TV, I remember this happening in a flat in London a few years back when I was watching the World Cup. Next door knew that England had scored about a second and a half before I did. It is. You knew something's happened. There is a delay. There is a frame. Now, we don't really, because live TV is live within a couple of seconds here and there, and rarely do you have such an issue to notice it. I was probably also a satellite delay in there as well and all sorts of things, but you're going to be very constrained by your latency here. So, although we're talking about compression, and there's a lot of good work starting, these are going to have to be very fast compression algorithms. And so we're unlikely to see the same sorts of compression rates that we get for MPEG encoding. You know, those very high, 20 to 1 and above type compression. I think we'll have to go some to find those, just purely because usually to get high compression, you take a large amount of data in any one time. That's usually how you do it. You have to grow the amount of data you take because you need to spot patterns within it. We're probably not going to be able to do that because of the latency that then adds into the system. And so, CPRI specifies up to 10 gigabits, and you can quite easily work out how to use that 10 gigabits very quickly. 20 megahertz and an 8x8 MIMO will use that 10 gigabit interface up without any trouble whatsoever before you add sectors on. So digital has its issues. I have lots of slides on this, but I won't labour the point too much more. So what about analog? Where has analog been used? Well, analog has already been used in some of these sorts of networks. Predominantly for places where traditional coverage was incredibly difficult, where you needed very high cell densities, which is exactly the sort of places we're talking about using these types of very high cell densities now. So you often find it for in-building distribution. So out of the department here, a company with Cambridge was spun out called Zinwave that delivers essentially repeater systems for distributed antenna systems within buildings. Over multi-mode fibre, as you will often find installed. In underground tunnels, in shopping malls. So if you go shopping in the Blue Water Shopping Centre in Kent, it actually has something a bit like a Cloud RAN. optical fibre distributing analog signals, in this case, around to various parts of the shopping centre, and all the mobile operators hosting their equipment, their base stations in a base station hotel within the premises. So these sort of systems exist, but they have always been rather in the niche for applications where the traditional techniques wouldn't quite work. But they are relatively straightforward. The optics, other than the linearization issues, which was much an electronic and a processing issue as an optics issue to some extent, have been developed to distribute signals over. But the big advantage is you only carry what you need, and you can carry as much of it as you need. If you're digitizing waveforms, as soon as you start your bandwidth starts going up, your data bandwidth explodes. It's not quite the same case with analog. And you can do all sorts of other sort of flexible issues. This was an experiment we did looking at this for multiple WiMAX signals delivered over what looked rather like a PON network, but with an amplifying at the front stage, and then a PON distribution with EPON data. And I'll mention at the end one of the advantages of what the issues might be if we look at these different types of network and how we might integrate with optical fibre we have already. So that's what a Cloud RAN looks like. We mentioned some of the advantages in terms of what that changes at the base station. But what does it allow us? What other does it allow us to do or to do better? Well, to think about that, we need to think about some of the technologies that are going to be driven into certainly the full LTE advanced standard, and we'll be looking at towards 5G. And all of the key things that seem to be coming through are actually about thinking differently about how this network is organized. Thinking differently of how we may take what was traditionally a base station sitting in the middle and only dealing with its cell and being an isolated part of the network that just takes data and spits it out and gathers data in and processes it and sends it back, to something that is a co-processing network, something where actually there are relationships between those base stations. And the data at different geographic locations means something and has co-processing. And these are probably one of the key technologies of how we're going to get anywhere near these boosts in data rate that we actually hear as the headline figures of 5G, this 1,000 times increase in data rate. So let's think about a user at the cell edge here. Now, this is typically the part of the network where you're going to have the lowest coverage. Now, what are sort of technologies are coming through? Well, one thing you may do is have small cells or het nets that give additional capacity in those areas. But this may just be a point where you wouldn't necessarily want that extra capacity. You're just at a borderline between two parts. So one of the first things we're seeing in LTE is the idea of cooperative multipoint. Now this in a way is distributed MIMO, essentially. You have two antennas, they're not next to each other, separated by a quarter of a wavelength anymore, they're in two distributed locations. But if I'm sitting in the middle, rather than being handed over from one to another, there will be a period where I'm visible to both of those base stations. The idea of cooperative multipoint is, well, can I use that information? Can I use the fact that I've now being received in two parts of the network to give essentially additional processing? And of course you can. We know that the maths of that is well known. What is more challenging is, well, yeah, that's cool, but MIMO is relatively easy when my two antennas are sitting next to each other and I digitize and I can do all the processing on an FPGA or an ASIC that sits all in one place. What happens if I know something here and I know something here? How do I co-process that? How do I work out that I know this, I know that? When it's waveform data, it's waveform level with two separate channels that I'm trying to co-process. That's not so simple. And calls on actually what very quickly becomes quite high data rate communications between these cell sites to swap waveform information about those two received signals to co-process, as well as the control and coordination that is needed to make that happen. And so actually Gerhard Fettweis in Dresden has done some field study trials of cooperative multipoint already. And you see that the data rate, as you put more cells and more users together, grows exponentially. And I know that's a phrase that marketers use, but actually in this case it is close to being true, as you have more of these units. And these links, this mesh of data links between cells, increases very rapidly. And that's something that we could well do with avoiding. So again, you think we've now actually have remote radio heads transporting, whether analog or CPRI. Now in front of our gateways, we can do some of this co-processing. And we're in the same point. We're receiving these signals. We'll have to factor out differential delays between these, but we can, PON systems do training of optical links down to 32 nanoseconds. So it's not without the technology to actually have very high synchronization between these parts. So this is the processing we do. And at the moment, this is data and CSI, so the carrier of the channel information over these links. But we could do much better if we can get around this low latency and high capacity requirement. You can also sort of flip that on its head a little bit. Of the other problem of being in between two cells is you're getting information from either side. Some of it you want and some of it you don't. So you're getting interference from other cells. However well you do your frequency reuse, there's always a certain amount of information. Can we coordinate how we do our resource allocation in the two cells when you're in the middle, so that you're not getting interference? This isn't quite so heavier use of the X2 interface, but still is a joint processing between our cells. And the final one is something that the wireless sensor network guys have thought about for a long time, but the mobile guys, with their very rigorous thoughts of "this is my spectrum, get off my land, you're not welcome here" attitude to spectrum, are only just starting to consider. We always worked on having nice little chunks of spectrum allocated up. It seems unlikely that there will be enough of that. There will be enough of a consensus on this to have nicely carved up bits of spectrum for 5G. There'll be reuse of 3G spectrum. It is interesting, the comment about 2, 3, 4, which was best. Well, we're already starting to see operators thinking about turning off their 3G networks, which gives you an indication of what they think about it. 4G will be for high data, GSM will be kept for calls and broad coverage, some machine to machine at low data rate, but the 3 is withering and we'll start reusing those frequencies. But I don't think we will have a set frequency. We will have some devices in short networks using millimeter wave bands. We'll have scattered bands throughout the microwave. How are we actually going to use them? Well, a lot of work has gone on in what's called cognitive radio. The idea of, can I sense the network and make decisions? Much of it is viewed around the idea that all of my terminals are pretty much ignorant of the rest of the network other than the little bit that they can see. Because in most situations, that's going to be the case. Except for the fact that if I'm taking a huge chunk of spectrum and transporting it back here for processing, actually, I could know an awful lot about the network, about the spectrum usage within my network. I could create almost a map of spectrum usage in real time if I'm taking a large enough chunk of spectrum. So if I'm collecting a huge band, transporting it back digitally, probably analog if you're taking that much, I could build an entire map. And we had a demonstrator here for a while that was looking on the Wi-Fi band, that we're picking up Wi-Fi bands and actually mapping out what the usage was. And that flips the game in cognitive radio. because we now do have network-wide knowledge of the usage of the spectrum, and it's by sensed, not by actually inference of what we can see and what we can't see at various separate locations. So you could have a model whereby actually we are going to be more reactive. We are going to be more adaptive in what spectrum we allow people to use. And if we have an underlying network that then can allocate that in various different ways, we could do an awful lot in how we essentially create a transparent underlying network for our system. Something that can vary the frequency it uses, can vary the capacity that it allocates to its cell, and most importantly do that in an agnostic way of whatever technologies are being run over the top. So actually the idea of having an E node be in an alien base station no longer becomes that much of an issue. They're one and the same to all intents and purposes, and could be aggregated in a single set of technology rather than being aggregated further behind. Okay. So this could be a resource of cloud function, this idea of having this network map. The final thing that I think is probably one of the most important things, if we actually look at how our base stations typically are used, it's very much a function of what region that base station is actually in. Is it in an office, a business environment? Is it in a residential environment? Is it a shopping centre? And you know, the classic one might be a sports stadium. You know, not much happens in a sports stadium throughout the week. There's the groundsman, there's a few people training. 3 o'clock on a Saturday, capacity goes through the roof. How do we deal with that? Well, at the moment, the only way we can deal with that is by putting rack units in a box at the base of the antenna. That's the only real choice we have. We have to capacitize each cell of the network for the capacity of that cell. But what could we do if we could extract that a layer and say, now I have a collection of cells, and all I need to put is enough capacity to capacitize that collection of cells for the peak at any one point within that part of the network. So the fact that this has a peak can steal capacity from the cells that are in this area that don't have a peak until later on in the day. So now, rather than having essentially to capacitize the green to the top, the purple to the top, the orange to the top, I can add up and integrate across those. And now all I need to capacitize is to cross these to whatever my average is going to be. And then I just need a network that allows me to decide where I'm putting my resources and how I'm going to allocate them to my different cells depending on what my cell requirement is at any time. I need very flexible remote radio heads. I need those that can manage multiple frequencies at one time. I may need quite wideband antennas and amplifiers, and that's another engineering challenge. But now I just rearrange my network, and I view my baseband resources not as something that I design when I build my network. I view them as a virtual pool that I can configure my network based on the movement of my traffic. Now that's not without an issue. Actually, once you start doing that, then working out where your traffic is as it moves around is quite difficult. And actually being able to have the function within your network to be able to see how your traffic is evolving is not as simple as it might first seem. Because one of the things you may do, the sports centre example, I may have 10 base stations around here. And I serve them all with one signal and make one big supercell during the week when no one's there. And maybe someone has forgot to tell me that Wednesday night there's a sudden last-minute international has appeared at this sports centre. So I start seeing my capacity of this supercell rising. How do I know where it is? I have no granularity in it. It's not a showstopper, but it needs some careful thought because it's a different way of thinking about how I have to tear that network down and reorganize it on the fly. Okay. But this all isn't without issue. And the biggest one, again, comes back to latency. Normally, my eNoB is required to turn around and respond an acknowledgement to my signal within 3 milliseconds. When this system was designed, no one expected that some idiot would come along and put a whole bunch of fibre in between the antenna and the eNoB. So, light travels quite fast. Perversely in fibre, not the speed of light, but 2/3 of the speed of light, but that's still pretty quick. But it does lead to reduction in my time, and I have to take everything into account that wasn't expected. So any framing, CPRI, compression, encapsulation, anything I do, that processing time has to be taken into account. And so I now put even stricter requirements on how quickly I'm responding to my acknowledgements. And most of the research we do in radio over fibre comes up against this as its main bottleneck. Now you'll see many papers who predict sending Wi-Fi over 100 kilometres of fibre. They're missing one small caveat in that particular criteria they give. They're sending the physical layer of Wi-Fi over 100 kilometres, and that's very easy. It's a cube OFDM signal, easy to do. What you actually find is that you can't send a native Wi-Fi signal over more than about 9.5 kilometres of fibre. Because what happens is, after that time, that round trip delay, your 10 microseconds per kilometre, when you get to about 100 microseconds or so, your Wi-Fi has not had its acknowledgement in time and so times out. So you can't actually extend that distance without extending the timeouts. And you can extend the timeouts, but actually in Wi-Fi you do that, you see your data rate dropping off because it isn't doing anything else while it's waiting for its air interface acknowledgements. TCP acknowledgements will carry on, but the air interface sits and waits. So if this is the way we're going, we need to build some of these longer latency, some of this acceptance of different ways of handling latency into the system. Because this is auto-corrected to hard, that should be a Q at the end. It's an ARQ, it's an automatic repeat request. So it's that's what happens when you do things on an iPad. It's a request. There are other ways of doing it, but you can find much better ways of doing this that actually are more accepting of some of these latencies without the user seeing the latency in the data rate. So the last bit I'll talk about is how might this all factor out? Well, fibre is rolling out to base stations. This is going to be an inevitable fact of LTE to a certain extent. There has been increases in the microwave backhaul, but the sort of data rates, even before you start factoring in CPRI, are going to call for more and more fibre being laid out. That works for larger base stations, but would people really run fibre out specifically to small cells? It depends where it is and what it's there for. I think in many cases what we are seeing though is that fibre is now out in the ground in most regions much closer to the users, the sorts of places you'd want to put cell sites, or certainly for small cell sites, in a way that it just wasn't 5 or 10 years ago. If you wanted fibre to those sorts of sites, you had to put it in the ground yourself. Now with BT's rollout, Virgin's rollout, Sky's rollout, you're seeing fibre at cabinets. Ideal sort of spots for small cells. So overlaying in PON is an ideal technology. Most PON out there is 1 gigabit, 2.5 gigabit. The current highest standard has just gone to a 40 gigabit PON. But if you're going to take up 1 gigabit, 4 gigabits, 10 gigabits even for a CPRI interface, you're taking up quite a lot of the bandwidth that was of a traditional link. You're squeezing the number of fixed line customers that are going to be on there. So maybe that's not the only way it's going to go. There are other ways of doing it. You can put overlay channels into PON. So actually, the optical spectrum on the fibre is not that heavily used. And in optical terms, these channels are huge. big wide bands to allow lasers to wander around in their frequencies. So there are opportunities to fit other overlay services in some of these optics bands, and I think that's certainly one of the European projects we're involved in is looking at how you do this. When you have very high density networks that provide a wavelength per customer, well, you can provide those wavelengths to anyone, whether it be to customers or to serve cell sites, to provide wireless backhaul to all sorts of aspects. And this is one point where it starts getting really quite interesting, how we think of, rather than having a wireless access network and, well, there's that optical stuff that just moves bits around for me, but we're not worrying too much about that, to something that is rather more integrated in the, do I really want to worry about whether I'm on Wi-Fi to a fixed broadband connection or my cell site or my wireless interface, and actually starting thinking of, well, we need transparent transport that sits underneath all of these access technologies. And I'm worrying less about whether I'm a 1 kilobit a second parking sensor or 100 megabits per second video download or a 1 gigabit per second tactile glove. Can I access different resources in ways that are meaningful to me? Okay. I won't talk too much about that. But what we're likely to end up with of sitting underneath, I think, is something that tries to change the way we think of an optical fronthaul. It would have been backhaul, but could still be backhaul, of integrating wired and opportunities to remove a lot of the functionality from those cell sites, pull it back to a point where we can have co-processing. And just as wireless, there will be, I'm sure, a suite of different options and different standards, it's likely that the optics are going to sit underneath, providing support to a huge number of different overlay standards that provide services. And that, in a way, is a good thing, but can also be a bad thing. Can also be, and total disaggregation between the two means that we don't actually leverage the advantages of either properly. And so they have to be, I think, co-designed when we look at designing the network. Okay. So we're seeing digital radio over fibre. The concept is being rolled out. I think there's still a role for analog in certain parts. But it will depend very much on how, certainly the community that's working on that can link it to the needs of the network and the needs that we see as in 5G for co-processing. So, thank you very much for your attention, and we'll take a few questions before lunch.